Welcome back to AP Statistics. This is Dr. Kling, still not affiliated with the College Board. I'm talking today about hypothesis tests. I'm going to try to give, I call this part 1 because it'll take at least a couple of talks to get through it. I'm going to talk today about sort of I'm going to try to give a very simple story about hypothesis tests with a sort of minimal jargon. And then in another talk, I'll introduce a lot of the jargon that surrounds hypothesis testing. So remember when we were doing confidence intervals, we described an interval around x bar plus or minus m, and we said the true parameter, remember x bar is the sample statistic, sample mean, and mu is the unknown parameter, the true population parameter, which we don't know. And we describe an interval around the sample statistic, and we say that it's very unlikely that we would have observed the sample statistic if the true mean were somewhere outside the interval. So we're talking in terms of intervals. And now I'm going to talk about, with hypothesis test, we'll talk about a particular point. And so we'll say if the true mu were here, and I'll put a question mark, if the true mu were here, how likely is it that we would have observed the x bar that we did? So that's sort of the question. So now instead of asking about an interval, we're asking about a particular point. And the interval, in confidence intervals, we calculated an interval in terms of natural units. So it could be number of calories or whatever. Now, when we do a hypothesis test, we're going to compute something we call a p-value, which is a percentile type calculation. And a p-value is the probability that we would have observed our x bar, our sample statistic, if a particular value of mu were true. Okay? So we're trying to say what would be the chances that we would have observed this guy if in fact this were the true population mean. And so we calculate that, and that's a p-value. So let's go with the example I was using last time with on hypothesis tests, where I think it was calories eaten by the typical 15-year-old. So we don't know what the true mu is. We got an x bar of 2800 in a sample of 100. And we're again going to be saying we have a known sigma of 400. And again, I'm going to underline that's a weird assumption, and that allows me to do the calculation differently than I'll be doing it when we have a more realistic case where we don't know the sigma. Okay, so the p-value is then okay, now what I need is a null hypothesis or an assumption about mu. So the question is the true population mean 3,000, or is it less than 3,000? So that's going to be what we're going to be testing. So the target mean is this, and we know we got something different from the target. The question is, what was the probability of our getting something this far away from the target given this sample size and given this standard deviation? So that's what we're asking. So we'll create a z variable. Z is equal to x bar minus mu over sigma over square root of n, or 2800 minus 3000, and our sigma was 400 over square root of 100. Okay. And I think that will come out to something like -5. That's a pretty big number. 200 divided by 40. Yeah, it's going to be -5. That's going to be a big number. It's going to give us a very low p-value, because the p-value is going to be the norm CDF from sort of -10 to that number. And it's going to be a very small number. We could calculate it. I'm sure it'll be very small, and I won't even bother calculating it. I'll say it's pretty close to 0, something like that. Now, so what that says is that it is very unlikely that our made up, remember I made up this whole problem, that x bar equals 2800 in a sample of 100 teenagers. So it's very unlikely that we would get that result if the true mu were 3000. It would be very hard to take a sample of 100 and get an x bar of 2800 if the true mean were 3000. Now we might have a very different story if the standard deviation were higher. Let's say the standard deviation, instead of being 400, were 1000. Okay, so we'll make a new assumption that the standard deviation is 1000. Now we get z is equal to 2800 minus 3000 over 1000 over square root of 100, and that's equal to, I think, -2.0. Okay, and that won't generate a absolutely tiny p-value. That'll generate a p-value, I think, of about, well, the p-value would be norm CDF from, let's say, -10 to -2. And we will call up a calculator. And yes, it comes out to about 0.0023, something like that. Okay, so by the way, with this emulator, it didn't like negatives inside the normal CDF, so I had to go from 2 to 10, or I typed in 100 by accident. Okay, get rid of that. So is equal to what did I say, 0.227. So still a very low probability that we would observe our sample results if the true mean were 3000, and so we would still be likely to conclude that the true population mean is unlikely to be as high as 3000. So that's kind of the basics of hypothesis tests. I'm going to next time introduce all sorts of jargon that has grown up in the history of creating hypothesis tests.